There we go. So if you put my face here, my video face in this blue square, you shouldn't miss any of the important content. All right. There we go. So I don't think I need to go over the hazards in too much detail, but when we have an explosive eruption in a Plinian regime or other regimes, we have a lot of the erupted tephra and gas injected high into the atmosphere, and we can we observe spreading ash clouds at many different heights that can pose risks for aviation, air traffic, as well as induce global cooling through the delivery of SO2 to the stratosphere. And then when we have dense collapse, we can generate pyroclastic density currents that can kill everybody in their path, so present deadly hazards for local communities. But also in the case of Mount Pinatubo in 1991, we saw that phoenix clouds rising from these gravity currents were able to deliver SO2 to the stratosphere. Okay, so a plan for today. We're going to start by going over some standard models for explosive eruption column regimes. And then I'm going to go over a couple puzzling features that have been observed in Plinian eruption deposits. Then I'm going to introduce the analog experiments we've been running here with multi-phase jets that attempt to simulate Plinian eruption columns. And I'll go over a tour of some of the characteristic features of jets in each regime. Then, using the results of these experiments, observations we've made, I'll introduce a new set of conceptual models for Plinian eruption columns and discuss how transitions among regimes may occur for a classic sort of eruption evolution. All right, here I'm going to introduce some standard column regimes. So these are what I would say representative images of explosive eruption columns in the Buoyant Plume, the partial collapse, and total collapse regimes. And below I'm going to introduce some conceptual model sketches that attempt to provide insight into the dynamics going on in these regimes. So in the first regime, the Buoyant Plume regime, this actually is probably the most commonly shown regime or conceptual model of an explosive eruption column, stemming from Pliny the Younger's first very nice description of the Vesuvius eruption in 79 AD. So here we have this relatively dense mixture of tephra and gas injected into the atmosphere from the volcanic vent at very high velocity. It's more dense than the ambient fluid, but it's driven high into the atmosphere with its initial momentum. So as this momentum decays due to the work of gravity, as it rises, the mixture develops turbulence on the jet margins, which begin to entrain ambient atmosphere and reduce the bulk density of the mixture. Now, in the case of the Buoyant Plume regime, this entrainment is sufficient so that the mixture undergoes a buoyancy reversal. And that's marked here by this dotted line marking the transition from the region that I'm going to call the fountain, where it's driven by its momentum, transitioning to a buoyancy-driven region, which I'm going to call the plume region. So from this height onwards, the rise of the mixture is driven by its buoyancy. And this is significant, particularly for the understanding entrainment into these two different regions. For example, in the fountain region, the entrainment has been found to be less efficient than it would be in the plume region. That has to do with the buoyancy of the mixture in the plume region augmenting entrainment of ambient atmosphere. Now this mixture continues to rise until it finds a level of neutral buoyancy, but even though it's driven by its buoyancy, it still has momentum, so it overshoots this level of neutral buoyancy into an overshoot region, and then this can collapse back down to spread into the umbrella cloud, and as it spreads, it can do this sort of undershoot, overshoot oscillation, kind of like a damped oscillation as it spreads in the atmosphere. So this is the classic Buoyant Plume regime, and this is one end-member regime for explosive eruption columns. The other end-member regime I'm going to introduce is the total collapse regime. So let's say we have our erupted mixture rise above the vent and it exhausts its momentum before it can go through a buoyancy reversal. In this case, it's going to collapse back down to Earth to generate ground-hugging pyroclastic density currents, and phoenix clouds lofting, elutriating fine ash from these currents can rise above PDCs to spread at some height in the atmosphere. Now we have this partial collapse regime, which hasn't received that much attention, at least initially when a lot of research began on coming up with regimes for explosive eruption columns. But in the past 30 years, there's been a lot of evidence mounting via numerical simulations, deposit analyses, and visual observations like this case for Calbuco here that show that this partial collapse regime indeed exists and eruptions do occur in this regime, and that they can occur in this regime for hours at a time. So it's not insignificant, and you can get significant deposition of material while the eruption column is in this regime. So in this regime, this is characterized by a combination of the key characteristics from the Buoyant Plume end member and the total collapse end member, in that we have simultaneous occurrence of a spreading umbrella ash cloud fed by a sustained eruption column, as well as intermittent or periodic PDCs being produced all on the flanks of the volcano. And in the case of Calbuco here, you can actually see in videos of this eruption, lower ash clouds spreading at multiple heights here. Some seem to be phoenix clouds rising from PDCs, others may be due to collapse occurring within this column here, generating ash clouds higher above these lower layers right around here. So the important point here, though, is that we have simultaneous occurrence of convective rise and dense collapse for a phase of this eruption that seemingly has unchanging source conditions, which is indicated by the relatively statistically stationary mean height of the eruption column. Albeit this overshoot region was also observed to oscillate, which is going to be important for later parts of this talk. Okay, so some evidence from deposits. Let's say we're looking at some deposits from eruptions for which there's no visual observations. What have we found? Well, Wes Hildreth and Judy Furstein did a stunning analysis of the Nova Rupta deposit in Alaska, and combined with recent work by Bruce Houghton and others, they found that in the proximal deposit near the vent, there's actually alternating layers linked to PDCs and to tephra fall from an umbrella cloud. Okay, so what this is implying is that you have either the eruption column alternating between the Buoyant Plume and total collapse regimes to in place alternating layers of tephra fall from an umbrella cloud and PDCs from collapse, or you have a sustained eruption column in the partial collapse regime generating PDCs intermittently or periodically while there's continuous fallout from the sustained umbrella cloud. And so in the past, some ideas when they first saw some of these observations of deposits, particularly for Nova Rupta, some people suggested that indeed you had the alternation of source conditions between the Buoyant Plume and total collapse regime. But more recent work, and I think they've revised in their 2012 paper with this regime diagram incorporating work from Bruce Houghton, that there's probably a partial collapse regime for this eruption column that emplaced this deposit, where you have fountaining along the margins here of material generating intermittent or periodic or perhaps continuous collapse. And then in the center of the column, you have material rising, going through a buoyancy reversal to convective rise to feed an umbrella cloud. Now, you had relatively steady source conditions because the distal tephra deposit on Kodiak Island shows evidence for this in a constant median grain size throughout the duration of this eruption that emplaced that deposit. And with this eruption, it was nice because there was a change in composition of the products of the eruption, the juvenile products, from rhyolitic to more dacitic and I think andesitic towards the end. So they were able to correlate layers in the distal tephra deposit with this proximal deposit layering to, in terms of stratigraphy, and then interpret from that the timing of the events. So the point here is that you had partial collapse with evidence of unchanging source conditions. Okay, so that goes against this idea, this proposition that it's alternating between Buoyant Plume and total collapse end members. Now there's further evidence for the existence of partial collapse regime, which was observed from Pinatubo eruption. In this figure up here, we see co-ignimbrite clouds rising from PDCs from a eruption column of Pinatubo that's either in the partial collapse or total collapse regime. In the proximal deposit, you see, again, alternating pyroclastic surge layers, which I'm just going to call PDC layers, that are interstratified with tetrafall layers interpreted to be from an umbrella cloud. So again, this implies simultaneous convective rise and dense collapse. Importantly, or interestingly, the inferred timing between PDC layer and placement within this interstratified deposit decreased from 24 minutes to 3 minutes upwards in the stratigraphy or later in time in the eruption. This was also the case for the Kilauea eruption, 800 BP. The inferred timing between PDC layer and placement decreased from 9 minutes to 3 minutes upwards in the stratigraphy, so later in time in the eruption. In addition, DeMuro et al. In 2008, in their paper, they analyzed this deposit and suggested that this deposit was in place by an eruption that evolved progressively from a fully convective column, so a buoyant plume regime, to a late fully collapsing fountain, so a total collapse regime, and that it passed through a transitional regime, which is, I'm calling the partial collapse regime, during this evolution. So by the end of this talk, I'd like to just, my new conceptual models are going to discuss this kind of evolution from buoyant plume to partial collapse to total collapse regime, because there's evidence that this occurs commonly for Plinian eruptions. Okay, and the last deposit feature I want to introduce are these quasi-axisymmetric terrace deposits that seem to be a common feature of submarine caldera deposits. So this is the deposit of Sumizu in the Izu-Bonin arc, and you can see on the topography here, there's these quasi-axisymmetric terrace features here, and they seem to be regularly spaced, as shown here, or quasi-regularly spaced by these radial profiles taken here and here, A and B. And this is a figure adapted from Tani et al. And when they set the ROV down to analyze this deposit, they found that the veneer here, the surface, was composed of unconsolidated and relatively large-sized tephra. Okay, it was products of the most recent eruption here. So suggesting that these terraces are related to the products of the most recent eruption. And this is the case also for Santorini and Macaulay caldera, where some seismic imaging has shown that this terracing is indeed present only in the surface layer here and not from layers interpreted to be from previous eruptions. Okay, so implications of these deposit features, I've mentioned these, I just want to go over it. Simultaneous occurrence of convective rise and column collapse when source conditions are assumed to be steady. The next is the interval between PDC layer emplacement seemingly becoming shorter in time. So the interval between PDC layers is becoming shorter, and this is occurring as we go later into the eruption. And then these axisymmetric terraces with their regularly spaced wavelength might imply that there's an intermittent or periodic process occurring in the eruption column, in the PDCs that flow from the eruption column, or in both that emplace these features. So we're going to use these to guide our investigation with our experiments. So with our experiments, what we've done in the lab here at UBC in our dungeon lab with no windows is we fill this meter cube water tank to about 70 centimeters depth with a linearly stratified, density stratified saltwater layers. So we, at the bottom, have relatively dense saltwater that decreases linearly to the density of fresh water at the top. And this is to mimic the density stratification of the atmosphere on Earth. And then we can characterize this through a Brunt by solid frequency, which characterizes the frequency at which, if you were to displace an object at equilibrium in the stratification from that position, it would oscillate at this frequency. So we inject a relatively dense multi-phase jet, and it's composed of sand and water or salt water to tune the interstitial fluid density of the mixture that we inject. And we are using coarse particles that have a Stokes number around 1 at the source. And this is because we're also trying to investigate how two-way coupled particles where the fluid influences the particle motions, but the particle motions also influence the fluid motions, how these particles can affect entrainment into these jets, which is important because if you don't have sufficient entrainment, you go through collapse. I'm not going to have time to talk about this much, but these particles also play a role in the collapse that we see in the dynamics of it, which I'll get to in a sec here. So we keep the source conditions steady throughout the experiment. It lasts for about a minute. The experiments are isothermal and obviously incompressible because we're using water. Okay, so just to return to our conceptual models here, we can see that at least qualitatively, visually, our experiments capture the overall features of each regime in terms of cloud spreading and sedimentation. In particular, though, what we've noticed is that the sedimentation along the margins of the jet in all of these regimes is not continuous. It is either intermittent or seemingly periodic. And we see these mixtures, these packages of mixtures collapsing intermittently or periodically, and we call these sediment waves. And they occur within an annulus around the jet that I'm going to refer to as the settling annulus. And I just want to define this because the sedimentation in this annulus is very complex, and we expect that this is going to lead to a complex structure to the deposit within this radius here. This settling annulus radius is set by the lateral extent of these sediment waves. And I'm going to show videos from experiments in each of these regimes and process videos where we highlight these wave fronts so you can see them more clearly. Okay, we see these sediment waves in all regimes, but they're most prominent in the total collapse regime. You can see here they're large and axisymmetric. We can also see them here in the partial collapse regime. They can be small or large in this regime. The small ones are not axisymmetric. They seem to occur on one side or the other. The large ones are axisymmetric as they are in the total collapse regime and reach the ground to spread as gravity currents. We see only small sediment waves in this buoyant plume regime, and they fall on one side or the other. They're not axisymmetric, and they disperse before reaching the tank base here. And just qualitatively, the way we classify our experiments into regimes, in this case, the mixture disperses before reaching the tank floor, so we consider that to be in the buoyant plume regime, whereas in the partial collapse and total collapse regime, these collapsing mixtures reach the tank floor, and in the case of total collapse, at least 90% of the injected mixture collapses to the tank floor before spreading into the tank. Okay, so to characterize the source conditions for our experiments, we're going to introduce two dimensionless numbers. The first is the particle volume fraction. This is just the particle volume over the total volume of the injected mixture. So you can think of it as the particle loading related to particle concentration. And then also the Richardson number. The Richardson number is basically characterizing the strength of the jet exiting the nozzle or the source. And it's the expression of the stabilizing buoyancy force acting across the jet boundary, which is opposing entrainment. So as you inject this relatively high velocity mixture into this stagnant environment, you create a Bernoulli effect that draws ambient air in, and this is initiating entrainment, and you have to overturn this density interface at this plume boundary to mix in this ambient fluid. Now you're bringing in light fluid underneath relatively dense jet fluid, so that's where the stabilizing buoyancy force comes in. It's opposing that, but if you have enough driving inertial force, basically velocity at the source, then you can easily overturn this density interface and mix in ambient fluid or atmosphere in the case of an eruption column. So with these dimensionless numbers, we can construct a regime diagram, which I'm showing here for our experiments. You can also construct this for natural eruptions. If you refer to Carrazzo and Jelinek 2012, they have their figure 3, I believe it is, where they show basically where ours and their experimental parameter space overlaps with those of natural eruptions. So with our qualitative determination of what regime each experiment is in, as well as measuring the source conditions, we can now shade in some colors to distinguish each of the buoyant plume, partial collapse, and total collapse regimes on this regime diagram. On the y-axis, you have the Richardson number in log space, and as you go up on this axis, you have jet strength decreasing. And then on the x-axis, you you have the particle volume fraction. Whoops, go back here. And you have particle volume fraction increasing to the right. So in pink, we have the Buoyant Plume regime. In green, we have the partial collapse regime. And in blue, we have the total collapse regime. And what we've observed is that as we vary the source conditions among experiments, so from this experiment, say here, to this experiment here, we see that the jet regime changes from the Buoyant Plume to partial collapse regime, and then from this experiment to this experiment where we decrease the jet strength further and increase the particle volume fraction, the jet occurs in the total collapse regime. So although we're not changing source conditions progressively along this trend through an experiment, we're populating what could be that trend with each individual experiment, and it's suggesting that there's actually a continuous transition from the Buoyant Plume to partial collapse to total collapse regime rather than an abrupt transition as the source conditions would change progressively. Okay, so I'm going to show some videos of these experiments. Let's see if this plays. There we go. So I apologize if the video is a bit laggy, but you can still see the general features. We have an umbrella cloud spreading here for this Buoyant Plume regime experiment, and you have sediment waves that are carrying the injected mixture below the umbrella cloud, actually at a length scale that approaches the overshoot length scale. But they disperse before reaching the tank base. When they disperse, they release the particles they're carrying that settle individually thereafter. And then the buoyant interstitial fluid in those sediment waves rises back up to spread in the umbrella cloud, or as you can see later in this experiment, the Phoenix clouds that I'm going to call this rising fluid, these Phoenix clouds actually rise and spread just below the umbrella cloud, which is an interesting result as well. And this, again, this is an experiment that's close to the Buoyant Plume partial collapse regime transition. Okay, so to highlight sediment waves, we came up with a technique, frame differencing. My friend Camilo actually suggested this. And what this does is we take the current frame, we subtract the previous frame, and it highlights the motion in between these frames. And what you end up with is a highlight of the sediment wave fronts. Okay, so you can see the sediment wave front has been highlighted here. So when we do this for our Buoyant Plume experiment, we can start to see the sediment wave fronts, although it's not super clear and easy to see. And also because of the spreading umbrella cloud and the 3D nature of the experiments, the sediment waves, when they fall through the umbrella cloud, they can be veiled and become less distinct. But they are there, we can see them and measure their velocity and radial extent. So this is the cloud that was produced by this experiment. And it was, let's see here, it is multiply layered. So as I mentioned, there were some lower layers, what I call Phoenix cloud layers that spread below this umbrella cloud, but the umbrella cloud itself also seems to be layered as well. Okay, let's go to the next one. So now that was this experiment here. Now we're going to decrease jet strength while keeping the particle volume fraction the same. And in this video, you can see, oh, I should mention that the fluid is pink and the particles are blue. And so where you see the blue is really the particle fluid mixture. So in this case, we have this umbrella cloud spreading here, but we also have lower clouds intruding later in the experiment. And you can also see the sediment waves more clearly here. And just ignore this fluid that comes out early. That's not having to do with the experiment. When the blue mixture comes in, that's really this beginning of the experiment. All right, so we have multiply layered cloud at many heights, almost approaching the tank base where they spread. And if we look at the frame difference images, we can see the sediment wave fronts are larger and easier to see here, okay? And I stared at this video for a long time, a year, maybe more, and convinced myself that I think these are periodic. And in my AGU talk, I actually showed some analyses of height oscillations and measured sediment wave frequencies that indeed show that these are periodic, especially the large axisymmetric sediment waves. Okay, so this is the resulting cloud. You have multiple cloud layers here. And this is the resulting deposit, and it may not be obvious at first, but there are actually faint terraces here that I pointed out with these arrows in this deposit and also on the other side. Whereas in the deposit for the Buoyant Plume regime, we did not have any terraces. So now we're going to move to this experiment here, increasing particle volume fraction and decreasing jet strength further to the total collapse regime. And you will see that the majority of the mixture collapses to the tank base, after which it spreads as a gravity current, and then after depositing its sediment, Phoenix clouds rise. And here you can actually see the sediment waves in this video. I don't even have to show you the frame difference in video version to see them, but I will anyways. So here you can see the projected area of the sediment waves on the camera is larger. They fall faster and are more frequent in this regime. So ignore this fluid up here that again was just colored fluid that was in the delivery tube before the mixture was introduced into the tank. So this is the main cloud layer that resulted, and this is basically a Phoenix cloud layer that might be composed of multiple layers or is a single layer and extends from about 15 centimeters down to the tank base. And this is the resulting deposit. So a top view here on the left, we can see these quasi-axisymmetric terraces that also appear to be regularly spaced, similar to what we saw with Sumizu. And then this is a true color image of this deposit, which I just really love because it's almost as if it's sunset on my new volcano edifice that I created in the lab. It looks beautiful to me. So you can see the terraces here. Although interestingly, as we get close to the rim here, we don't see the expression of terraces so easily. That could have to do with the angle repose of this sediment. So now if we look at the deposit from a total collapse experiment that had a relatively high total mass of particles injected compared to that previous one, we actually see that we're starting to build a cone at the angle of repose of the sediment. So you see some outer terraces here, but you don't see any here because this sediment, if there were terraces, they collapsed because they were approaching the angle of repose of the sediment, not sustainable. I do think, though, that this cone is probably burying terraces that formed earlier in this injection, in this experiment. Okay, so I'm going to do a recap here from these qualitative observations, but also quantitative. I'm just not showing the figures, the measurements of sediment wave size and velocity. But we do indeed see that in the total collapse regime, sediment waves are large, axisymmetric, and fall very quickly relative to other regimes and more frequently. You also have small non-axisymmetric sediment waves that fall in between, but in the total collapse regime, most of the sedimentation is occurring via these large sediment waves. As we change the source conditions to go through the partial collapse regime, sediment waves they're still large and small ones. They don't descend as fast as they do in the total collapse regime, and they're not as frequent. And then when we get to the Buoyant Plume regime, they become small. There's no large axisymmetric ones, and they disperse before reaching the tank floor. In fact, measurements have shown that their speed decreases to the terminal settling velocity of the particles they carry about here, where we visually observe them to disperse, which makes sense. When the mixture is decreasing in speed to the terminal settling velocity of the particles, it's going to allow the particles to decouple from the mixture and then settle individually thereafter. Looking at cloud intrusions, we can see the progression here through regimes. Here in the total collapse regime, we have predominantly spreading via Phoenix clouds into a Phoenix cloud layer. And as we move the source conditions to the partial collapse regime and Buoyant Plume regimes, we see that we now have an umbrella cloud and Phoenix cloud layers. And then as we go closer to the Buoyant Plume regime, these actually spread at more similar heights to the point in the Buoyant Plume regime where they are almost indistinguishable, yet there's still multiple layers here. Now, for the deposit, we see axisymmetric and regularly spaced terraces in the total collapse regime, but these become more faint as we move source conditions to the partial collapse and Buoyant Plume regimes. So some conclusions from these observations of our experiments is that as the source conditions change, our multi-phase jets seem to transition continuously in their behavior from the Buoyant Plume to total collapse regime through the partial collapse regime, as suggested by DeMuro et al. For the Kilauea eruption. This transition is occurring in our experiments primarily through the dynamics of these sediment waves, which we have shown to be periodic. I showed this in my AGU talk and can show some figures from this at the end here. And these seem to fall from the top of the jet, so the overshoot region or level of neutral buoyancy. And then as jets evolve from the partial collapse to total collapse regime, as we vary the source conditions among these regimes, the sediment waves become larger, they fall faster and occur more frequently. And in the total collapse regime, the concentric rings or terraces that we see are most pronounced, whereas in the partial collapse regime, they are less distinct. So now what if we add fine particles that simulate ash, a more realistic particle size distribution for our eruption column analog? Well, we see for this total collapse experiment with fine and coarse particles that we have collapse leading to axisymmetric gravity currents spreading from the source or the column base, and phoenix clouds rising carrying the fine particles to spread at some level of neutral buoyancy into a phoenix cloud layer. And as this occurs, the inner jet core fountain is obscured. You can't see it anymore. In this case, we can still see the top, and we can see oscillations of the top in radius and in height. And we've actually done measurements to show that those oscillations are related to the ratio of the buoyancy flux and the momentum flux introduced at the source, which predicts the frequency of these oscillations, which we think are related to the occurrence of sediment waves and therefore periodic collapse of these jet columns. So when we let the particles settle over 2 days, the fine particles that is, they mantle with a uniformly thick layer, a terrace deposit proximal to the nozzle. So even though we have fine particles here in addition to the coarse particles, we still get terracing in the proximal deposit for an experiment in the total collapse regime. All right, I gotta wrap up here. So what about these new conceptual models? Well, I've made some model sketches here informed by these experimental results. And here I've shown these very busy model sketches below each regime image from an experiment. So on the bottom here is kind of incorporating the regime diagram that goes with these model sketches with this arrow here. So as we go from buoyant plume to total collapse, the Richardson number and the particle volume fraction are increasing, which means the jet strength is decreasing and the particle volume fraction is increasing. And now I want to go through a buoyant plume partial collapse, total collapse evolution, because there's evidence that eruption columns often go through this evolution, or they'll go through, for example, a partial collapse to total collapse evolution, which could have been the case for Pinatubo. So here in the buoyant plume regime, using insights gained from our experiments, we see that, yes, we have our found region and plume region and overshoot region, but this overshoot region seems to oscillate in height, and it generates non-axisymmetric small sediment waves that carry the erupted mixture below the umbrella cloud, and in some cases well below the umbrella cloud, so that when the buoyant interstitial fluid, the gases that is, and also fine particles that don't disperse from the mixture, when they rise again, they can intrude in lower cloud layers below the umbrella cloud that I call phoenix cloud layers. Or in some cases, they can rise to spread at the same LMB as the umbrella cloud. Now, the important thing here for deposit interpretations is that if you have sedimentation within the settling annulus occurring primarily through the action of sediment waves, even though you have individual particles settling below where sediment waves disperse, you're going to have waves of particles being delivered to this settling region, right? So you're going to have a sediment wave come down, it's going to release its particle load, and you're going to have individual particles settling, so you might get some separation of sizes, but it's still going to be coming in waves of individual particles settling, if that makes sense. Now, if we move to the other end member, the total collapse regime here, we're going to have sedimentation predominantly through large axisymmetric sediment waves falling from the top of the jet, and the top of the jet will oscillate as these grow and fall. And this is going to lead to terracing, axisymmetric deposit terracing within the settling annulus, but only if the topography that it's placed on is below the angle of repose of the particle size distribution in these layers. So on steep volcanic edifices, I don't expect terracing to occur. Now, in the partial collapse regime, things get very complicated. But some predictions I want to make here is that at this fountain, we expect sediment waves to fall from the fountain plume transition height, which we also expect to oscillate due to fountain dynamics. And then we expect large axisymmetric sediment waves to fall from this transition height. And then we expect small non-axisymmetric sediment waves, which I need to change this figure actually, to fall from this overshoot region similar to the Buoyant Plume regime. So again, it's a combination of the characteristic features of the end member regimes occurring simultaneously in this partial collapse regime. And we also expect Phoenix cloud layers to spread from this transition height and also rising above gravity currents from sediment waves reaching the ground. Importantly, this partial collapse regime with steady source conditions yet unsteady processes occurring in the eruption column can lead to alternating PDC tephra fall layering in the proximal deposit, even though source conditions are relatively unchanging. Okay, so this is a way to explain some of those deposit observations I introduced in the beginning. Now, I'm just gonna add a sort of alternative regime models here because our experiments are isothermal, so the Phoenix clouds that rise over our gravity currents are not generating buoyancy through entrainment, even though in the real case they could retain temperatures close to their magmatic fragmentation temperatures, as maybe was the case for Pinatubo. So in nature, when Phoenix clouds rise in the partial collapse and total collapse regime, they could rise all the way back up to where the umbrella cloud is spreading in the case of the partial collapse. And in the total collapse regime, they could rise all the way to where the top of the inner fountain is, or even higher. So this could have been the case. Either of these regimes could explain observations that I showed previously for the Pinatubo eruption. Okay, I think I'm out of time, so I'm gonna leave it there, I think. I've said all this. And then the last, actually, I do wanna show this, Matteo Cerminara and Tommaso. When we were at Mount St. Helens, Tommaso and I were around, and this was for the IFC meeting, we were around the campfire showing each other videos of his simulations and my experiments, and we interestingly both noticed that there were sediment waves in both. They were seeing sediment waves in their simulations of Calbuco, which you can see here. There's the expression of the waves here, and it's going to rotate around later in this simulation. You'll be able to see them better. And they seem to be coming from the oscillations of the overshoot region. And when we showed this to each other, I had met them before. I had no idea they were doing this work. And so we saw that these observations were being made in our experiments and simulations independently, but at the same time. So this is promising, I think, for the occurrence of sediment waves in natural eruptions. And then I think I'll end there and start the question period.
Thank you, Yoshi. That was great. We definitely have time for discussion and questions. If you'd like, please just go ahead and use the raise a hand function. I see Michael has a question.
Yoshi, that was fantastic, both the presentation and the experiments. I'm a bit puzzled about why you see terraces forming. What is the process that gives rise to the very discrete end that makes the stair-step type structure?
Yeah, that's a really good question. And I think when we run new experiments, we're going to try to instrument that proximal region of the deposit better, maybe perhaps with a scale that can capture the flux of mass as it hits, and also close-up video, because I don't have a concrete answer. But what I can say is that, we define the settling annulus as the lateral extent of the sediment waves as they fall. And we've noticed that the radius of the outermost terrace falls within that settling annulus. So I think what that implies for our experiments is that when the sediment wave impacts the tank base, most of the coarse particles are being deposited immediately upon impact. Now that it might be deformed further by lateral flow. And actually, you know what? I have a slide that I think is going to provide some insight here. So we ran some experiments previously with caldera nozzles, and this is in my paper with David Jessup from 2016. And actually, in all these experiments with caldera nozzles, they were mostly in the total collapse regime, and they all produced terracing. However, we ran this experiment with relatively low total mass of particles, and you can see these regions that have less particles deposited in between the rings or terraces. So actually, I'm not even sure if I should call them terraces, maybe concentric particle rings. And what this may be implying is that when the sediment wave falls, perhaps due to entrainment and vorticity in them, the particles actually concentrated in the middle of that toroid, which is the shape of the sediment wave. And then when it hits the tank floor, it concentrates all the particles in that ring. So it could be the terraces we're seeing in the experiments I showed you guys are actually rings, but there's a bunch superimposed upon each other to make them look like terraces. Now, one thing we want to do in the future is add a more continuous particle size distribution. And it'd be interesting to see if you get such an abrupt cutoff in thickness with these terraces if you have a more continuous particle size distribution. Also, I should mention that Greg Valentine's work, modeling work, shows that even with compressibility effects, what they found is that that'll modify the critical particle size that can be carried by the lateral flow after impact. But I think even with the compressibility effects considered, you can still perhaps get terracing to occur. Now we see these in submarine deposits probably because they're more easily preserved, whereas on land you have lots of weather and erosion. So maybe they're occurring, maybe not on land. I don't know.
Thanks, Yoshi. We have a couple questions that'll be audio and a couple that are on chat. I'll just kind of interleave these. The first question that I'll read here is from Leif Karlstrom, and he writes, why is the pink jet fluid phase in the partial collapse regime appear so dispersed relative to the other two regimes? And he further writes, is this modifying the background stratification that settling sediment interacts with? And you can see the chat questions too if you want to look at them. Yeah,
so let me go back to a picture of it. Go back here actually. So I think if I understand correctly, by dispersed, you mean dispersed over many different, a large range of height here. And I think that this is because we have small sediment waves and large sediment waves occurring simultaneously, and they can disperse at different heights. And actually some other qualitative observations I didn't show is that when you focus in on the sediment waves as they fall here, you get sediment waves that disperse before they reach the tank floor in this regime and then release their fluid to spread either at that height or slightly above. You get large sediment waves that carry this pink fluid to the tank floor, spread as a gravity current, then release Phoenix clouds. And those two different fates involve a different overall mixing history with the ambient stratification. So therefore the buoyant interstitial fluid is going to intrude at different heights just because of the different path it took via the small versus large sediment waves. I do think the stratification is indeed modified by the experiments, and we have some experiments where we actually measured the stratification after because we want to look at how much energy went into mixing the stratification. I haven't had a chance yet to analyze that, but I think that the primary reason for all these different layers here is because you get two different kinds of sediment waves. And then in addition, as Phoenix clouds rise from dispersing sediment waves, they can mix and modify sediment waves falling after. And then it gets really complicated to disentangle the effects on the spreading height of clouds and whatnot. Yeah, well, that's great. I had a similar question that last video you showed where you had the fine particles included. It seemed like you had the highest height at the initial, and then the height decreased as you changed the background. And yes, so with all with all our experiments, they go through. Actually, I'll just show you a height time series that I have here. I show this. Yeah, so especially with the total collapse, you get the highest height initially because you're injecting into a quiescent environment. But then once you start to have collapse, you're building this volume above the jet column, especially in the total collapse and partial collapse regime. And it wants to sink due to gravity, but it's being supported by the jet column, but eventually grows to such a size or weight that it can push the jet column down, and then it's a fluid, so it deforms and falls around it. That's basically a conceptual model for how these sediment waves are forming and descending. So we often see, and for the partial collapse regime as well, that you reach this max height initially in this transient, and then you reach this steady state phase where you approach a steady mean height, but you have oscillations about this height. But in the buoyant plume regime, we don't really see this initial max height. It kind of reaches its spreading height or max overshoot height and stays there, because you're not really building these large sediment waves, I think, to suppress the column and create large scale oscillations.
Thanks, Yoshi. Why don't we go to one of the raise a hand questions? Alexa, you have a question?
Hi, Yoshi, thanks so much for this talk. These experiments are great, and they certainly seem to be replicating some of the complicated features that we see in the geologic record in the Arunui eruption and also in numerical simulations. So I'm particularly intrigued by the sediment waves that you're generating in the buoyant regime. And I wondered, have you ever seen the sediment waves actually reaching the ground, or do they mainly re-entrain and become buoyant again before they hit the ground?
Yeah, that's a really good question. I'd like to run more experiments that are kind of near that buoyant plume partial collapse transition in terms of the source conditions, because as I was mentioning to Leif's question, this complex interaction between rising phoenix clouds and sediment waves in this settling annulus region, we also see interactions between sediment waves. So, and in the buoyant plume regime, we indeed see that you can have a sediment wave falling, and then one falling not too long after and actually catches up to it and merges with it. And I think this is causing them to then fall to a lower height than they would if they fell independently. So I definitely have several observations of that in this particular experiment that I'm showing here. And I think that leads to some of these relatively low undershoot heights that get close to the tank base. I think, to answer your question, I think as the source conditions get close to this transition, yeah, you're going to get more of these interactions that can maybe nudge sediment waves to actually reach the tank floor or the ground in the case of a real eruption.
So one of the interesting implications of that is that in an ostensibly buoyant plume, which we would visually observe or characterize as a totally buoyant eruption, you could potentially get processes that create pyroclastic density currents in the deposits that weren't from any of these other processes that we've previously sort of thought of.
Yeah, I think a big question I have is, and especially related to Matteo Cerminara's simulation that I showed, we see those sediment waves coming off the overshoot region. Do they see merging of those sediment waves ever in their simulations? Can you basically get small sediment waves from the overshoot region to actually collapse all the way to the ground and then generate pyroclastic density currents?
Right. And something that's difficult to tease out in the numerical simulations is when we have a sort of dynamic collapse of a sort of fountaining regime versus something that is truly buoyant the entire time. Buoyant in a traditional sense. So yeah, that's great. And just a follow-up question, have you been able to tease out the role of grain size on the development of these sediment waves?
Yeah, so I ran some experiments with most of these experiments are just with the coarse particles, because when we have the fine particles, you can't see the inner jet column. It gets veiled, and then it's harder. You can't really see if sediment waves are occurring. But we did run experiments with just fine particles as well. And we do see undershoots similar to what we saw in this buoyant plume regime here. And in fact, for some of the fine particle experiments, and Mark and Guillaume observed this in their 2012 paper as well, that there seems to be a lake collapse. So in their experiments, they had just two layers, a fresh and a saltwater layer and a fresh layer with a hard interface. And all of a sudden there would be a catastrophic lake collapse in some of their fine particle experiments. Now, when we run it in the linear density stratification, what I've been observing is that the undershoots get lower and lower with duration into the experiment to the point where they begin to reach the tank floor. So I've had this question that, okay, once you have enough material falling via sediment waves next to the jet column, you must have some re-entrainment of those particles, for example, and that should result perhaps in a lowering of the mean height and also maybe increase the propensity towards collapse. And I've been wondering if, okay, if you get a certain amount of undershoot, do you start to put the eruption column on a positive feedback cycle sort of path towards collapse? And in the future, we're going to try to run experiments where we can actually change the source conditions during the experiment, as well as vary the particle size distribution and or the color of the particles. And the goals of this are to actually go through this whole evolution in one experiment, and then by introducing different colored particles, maybe linked to their size, pull slices out of the deposit to look at stratigraphy and whatnot that results. So this is the grand new plan, if COVID lets me go through with it.
That's great. Thank you so much.
Yeah, thank you.
All right, Ben, do you have a question? Ben Andrews?
Yoshi, thanks again for a very nice talk. I was wondering if you could tell us what controls the length scale of the sediment waves in the fully buoyant scenario. Thanks.
Yeah, so I think actually Andy Woods, with his postdoc, Gotti, I forgot his first name, but they published a paper in 2016, and as well as Hunt and Burge 2015 do a review of fountains. And that provides insight for the fully convective buoyant plume regime, because the overshoot region is really a fountain, right? Even though it becomes fully buoyant, once it passes that level of neutral buoyancy, it's again a fountain. And there's different regimes of fountains depending on the Froude number, which is basically the Richardson number at the LMB of that overshoot fountain. And they provide scalings in the Hunt and Burge paper that predict the oscillation frequency, but also answer your question in that the maximum eddy size is set by the diameter of that overshoot region. So we think that the radius or diameter of the sediment waves is going to be set by the diameter of the overshoot region, particularly at its top, because that's going to set the maximum size of eddies, for example, that are probably playing a role in these small sediment waves. In fact, I think we did a close-up of that overshoot region for a buoyant plume experiment, and it seemed that some of these small sediment waves actually have vorticity as they fall off the top, almost as if some of them are actually spalling eddies that have entrained particles spalling off the top. So I think the diameter of those small sediment waves is set by the overshoot diameter. And then in turn, the radius of the settling annulus is therefore set by the diameter of the overshoot region. And one dream I have is that this maybe can be linked to the lateral extent of terraces, so that if you have an ancient eruption and you see terraces, that might be telling you some information about the actual eruption column geometry, especially at the top.
Thanks, Yoshi. Looks like Uli has a question.
Hey, Yoshi.
Hey, how's it going?
Not too bad. Evening over here. Question, you showed that sometimes you have substantial asymmetry in your 2D observation of your columns.
Mm-hmm.
I wonder, what do you think could be an extra influence at the same feeding conditions, but if you have an irregular, let me call it volcano, cone, crater, whatever we call it, morphology?
Yes. I forgot whose talk it was. I saw at HU who was doing experiments with like one side of the vent higher than the other. Is that what you're referring to? Yeah, that was you guys, right? Okay. So yeah, I think what that's going to do is it's going to change the initiation of entrainment. So it's going to create an asymmetry initially in entrainment into this fountain region. And I think what that could do is you could actually, I mean, it depends, because some experience we did with David, Mark, and I, when we had like a linear vent, we found that, yes, the initial jet coming out of that linear vent had that same vent geometry, but that I think 15 or so or 10 or so jet vent diameters above that, it actually became axisymmetric. So the cross section became circular, even though the vent was linear. And that's because the turbulence tends to equilibrate the mixing in the mixture. So I think that you might originally get some asymmetry and entrainment, And then it's a question of how high does it rise before it exhausts its momentum in terms of, does it recover axisymmetric structure, or does part of it collapse because you have different rates of entrainment on either side? So do you get collapse of, say, the side that has less entrainment, or so the side that erupts of the jet on the side with the higher part of the edifice, you might get inhibited entrainment because it doesn't develop as soon in the jet rise, whereas the side with lower crater rim might have entrainment start earlier. So that might be more likely to become buoyant, whereas you might be more likely to have collapse on the side with the higher crater rim. That would be my shooting from the hip answer.
Right. Thanks.
Well, thank you, Yoshi. That was a great talk and great discussion afterwards. I think we should thank Yoshi now. I think there's a lot of opportunity for discussion further, and I've posted on the chat the Slack invite if people want to participate in Slack later on. So thanks, Yoshi, and everybody join us next week. As usual, I'll just kind of leave this channel open, the Zoom channel open, for those that want to have a little bit of after discussion if you want to hang out for a second, Yoshi.
Sure.
And Yoshi, I'll also provide, one of the things we do is we record this, and I'll provide you a copy of the recording. Among other things, it has a recording of the chat, so you can kind of look at that. I know it's hard to keep track of that while you're talking at the same time.
Oh, that's great. Thank you. Because I always have this issue where I want to listen, but I also want to take notes, because these questions provide a lot of really good insight.
Hi again. That was, again, a very nice talk you gave. I know that Greg Valentine wanted to be here. He's somewhere on the road right now, but I think if you can send him the link for the talk, I think he'd like that, or maybe Joe can send it or something. So.
Yeah, I will do that for sure. And then we hope to have the manuscript we're hoping to submit, a big manuscript, by the end of the month, and then hopefully it'll be published by the end of the year. And with that, the experimental data set and supplemental videos as well. But yeah, I'm really excited for the new experiments that we want to design, because these, in some ways, these are a bit crude in terms of the source conditions. You may have seen some bubbles actually in some of those experiments, which have been such a bane for me, but because we have to mix the mixture quite vigorously to keep those coarse particles that, you know, they have a settling velocity that's close to the turbulent velocity of the mixture when we're mixing it. So we have to mix it extremely vigorously to keep them homogeneously dispersed in the delivery bucket. And when we do that, we end up entraining air sometimes, especially when the bucket water level goes down towards the end of the experiments.